So, today we will learn about vibration of a molecule. Vibration of a molecule, we have seen the rotation of a molecule and corresponding energy levels and spectral lines. So, vibration of a molecule, in this case also this the molecule has to have permanent dipole moment, then it will be infrared active. So, it is similar to rotational of a rotation of a molecule, rotational spectroscopy, as well as it is called microwave spectroscopy. So, in case of vibration of a molecule, so we get basically vibrational spectroscopy. Or it is called infrared spectroscopy. So, some molecules are infrared active and some are infrared inactive. Infrared active molecule, so which are having the permanent dipole moment. So, this for this case, that molecule should have permanent dipole moment, okay, and it will be infrared inactive, when molecule will not have, so no dipole moment, in this case no dipole moment, okay, or better it is to say that there should be change of dipole moment, fluctuation of dipole moment due to vibration. If so, then it is infrared active molecules. If there is no change of or fluctuation of dipole moment during vibration, then it will not be microwave active molecule. Okay. So, we will give example that like this, we have seen that in case of hydrogen chloride. So, this two heterogeneous nucleus, basically heterogeneous nucleus having the permanent dipole moment. So, this sodium, hydrogen and chlorine. So, it has permanent dipole moment. So, it is infrared active. Similarly, sodium chloride, okay. So, it has permanent dipole moment. So, basically in this case it has permanent dipole moment. Okay. So, obviously it is microwave active, but sometimes this molecule it do not have permanent dipole moment, like say carbon dioxide. Okay. Say carbon dioxide, it has no permanent dipole moment, but due to vibration it may happen that there will be induced dipole moment, and with vibration or with time this induced dipole moment fluctuates, and then that molecule will be infrared active. So, in case of permanent dipole moment, there is no question that all the time it is microwave active, infrared active, right. In case of infrared active, so this molecule as a, so in this configuration it has no permanent dipole moment. Okay. So, that you know why it has no permanent dipole moment. So, here is minus 2 delta charge, here minus 2 delta charge, okay, here plus 4 delta charge. Okay. So, or I can, or if you think, write this minus delta and this minus delta, then one can write this. Okay. So, that is charge balance. So, now dipole moment here. So, direction is positive to negative direction. So, direction is in this direction, and here positive to negative is in this direction. So, this equal dipole, equal magnitude, but having the opposite direction. So, net dipole moment for this carbon dioxide is 0. Okay. But if it vibrates, if vibration is symmetric, means this oxygen, they are vibrating, okay, keeping this carbon at the middle. Okay. If vibration is symmetric, means this oxygen is, when it is going this side, so this oxygen also going the same direction. Okay. Yes. So, what is happening? It is going this direction, it is going this other direction. So, in this case, or just opposite way, so what is happening in this case, dipole moment, so it is going this side, so length is increased, so the dipole moment will increase. Okay. And in this case, this distance length is decreasing, it is going this side. So, its dipole moment will be smaller, this side dipole moment is smaller, this side dipole moment is higher. So, there will be, so direction is of course in opposite direction, but now magnitude are different. Okay. So, it will show net dipole moment due to this, basically this this oscillation, this vibration. Okay. So, if it vibrates like this, that it is going this side, it is going this side. Okay. So, same things. So, this will increase. So, dipole moment is higher, this will decrease, dipole moment is lower. So, net dipole moment in this direction. Okay. So, due to this either vibrating in same direction, okay, either this way or that way. So, in this case there will be induced dipole moment which will change with time. So, that means there will be fluctuation of dipole moment with time, as I have shown in case of rotation, okay, in same way. So, this fluctuation with time, actually if you plot, so this fluctuation is will be like this. So, it will interact with the infrared, and that is why it will be infrared active molecule. Okay. So, if this vibration is different way, say, so it was in same direction. Now, if it is in opposite direction, so when it is going this side, other one is this side, or other way, when it is going this side, other is going other side. So, it is basically now it is going this side and this oxygen is coming this side. So, basically compressed. So, this basically now they are coming towards carbon. So, dipole moment magnitude will be different for each one. Okay. So, total dipole moment will be, then there will not be, total dipole moment will be 0. There will not be any net dipole moment. Okay. So, other way, when it is stressed, expanded, vibrating this way, going this other side. So, this also increase, dipole moment increase, this also dipole moment increase, and dipole moment are in opposite direction, they are same. So, then it will not be, again there will not be any net dipole moment. So, this called basically symmetric vibration. Okay. This called symmetric vibration. Symmetric vibration of the molecule, and in case of symmetric vibration of the molecule, there will not be any induced dipole moment, or there will not be any fluctuation of dipole moment with time. So, this molecule, in that case it will be microwave inactive molecule. Okay. And in this case, this is called basically symmetric asymmetric vibration. This is basically asymmetric vibration. Asymmetric vibration. Okay. So, in case of asymmetric vibration, there will be change of dipole moment, fluctuation of dipole moment with time. So, then it will be infrared active molecule. Okay. So, it depends whether it will be infrared active or it is not infrared active. In case of no permanent dipole moment. So, for those molecules which are not having permanent dipole moment, for that molecules also sometimes it is infrared active, it may become infrared active when they will have asymmetric vibration. If they have symmetric vibration, then it will not be infrared active molecule. Okay. So, from infrared spectroscopy or vibrational spectroscopy, one can tell about the vibration of the molecules, whether this molecule is vibrating symmetrically or it is vibrating asymmetrically. Okay. So, also this vibration may not be only this in along the straight line. It may be this dipole moment change or induced dipole moment or fluctuation of dipole moment. Okay. It may happen due to bending of the molecule also. Okay. So, in this case, if it vibrates, oscillates like this. So, if starting is this, then okay, then again comes straight, again comes straight. Okay. And next step, it is if it okay. So, if this way also it bends. Okay. So, this carbon atom now 2 oxygen. Okay. Now, if it bend going straight, again bend. Okay. If due to the bending of the molecule with time, this also will give the induced dipole moment, and there will be fluctuation of dipole moment with time. Then also it will be microwave, or in case of vibration it is a infrared active molecule. Okay. So, due to vibration or due to oscillation in terms of bending or in terms of asymmetric stretching and compression, okay, there will be induced dipole moment, and due to this induced dipole moment or due to the fluctuation of dipole moment, fluctuation of induced dipole moment with time, the molecules which are not having permanent dipole moment, they are also infrared active molecule. Okay. So, that generally in case of rotation, it is only the molecules which are having permanent dipole moment, only those molecules are microwave active. But in case of vibration of a molecule, although there is some molecules do not have permanent dipole moment, but due to the asymmetric vibration or this bending of the molecules, so this induced dipole moment fluctuate with time and it become infrared active molecule. Okay. So, now vibration of a molecule. So, basically one has to understand that this one atom is here. Now, if you bring another atom towards this atom, so they form molecule keeping them, these two atoms, in equilibrium distance, and that distance is called bond length. Okay. So, what will be the equilibrium distance? That depends on the force. Two type force will act here. One is, say, this is nucleus, and here distribution of electrons in this molecule also, this say nucleus, and this distribution of electron. Okay. Now, when they will come closer, then there will be electrostatic force between these two atom. So, two type of force will act. One is attractive force, so source of attractive force will be this electron interaction and nucleus interaction. So, this source of attractive force, sorry, so this it is just opposite. So, let me write this repulsive force, source of repulsive force, electron interaction and nucleus interaction. Okay. So, these are positive charge Jd plus Jd plus Jd, and this is the negative charge electron. So, there will be repulsive force. Okay. And then attractive force, there will be also attractive force. Source of attractive force is basically electron nucleus, and also this for this atom, this nucleus to this electron of the other atom. Okay. So, nucleus to electron, that interaction basically it will be attractive force. Now, when you are bringing them closer, so this force will balance, these two force will be equal at a particular distance. Then that's it, at that distance basically we tell the total energy of this molecule will be minimum. So, generally this energy, this curve is like this, it's generally varies like this. Okay. So, if here is one molecule and another molecule, you are bringing towards this. So, this is the R. Okay. This is the R and this is the energy. Okay. So, this energy changes like this. So, when you are bringing, so energy is this, it's very small. Okay. Then it changes like this. So, energy become minimum, and further if you, so this distance, if I tell this distance is R0. So, when distance is greater than R0, the energy is higher. If less than R0, energy is higher. Okay. But in this side, if you see that the change of energy is very sensitive to the change of the distance. So, that means these two molecules from equilibrium position, okay, if you try to bring more closer, so the change of energy is very high, rate of change of energy is very high. On the other hand, if you go this other side, if you try to take away from the equilibrium distance, then its energy also increases, but rate of change of increment is slow. Okay. So, this force is basically, or this energy change is basically is not symmetric, it is asymmetric. Okay. So, this the r0 is the equilibrium distance. Now, from equilibrium distance, if you try to change the distance, then its energy will change. Its yes. So, it will happen during vibration. So, vibration of a molecule, basically for a diatomic molecule is in a equilibrium position, they have bond length, equilibrium distance is r0. Now, when they will vibrate or symmetrically or asymmetrically, okay. So, then their energy will change, and that energy basically potential energy. Okay. And this potential energy, if you compare with spring mass system, so this force basically you can write F equal to like spring mass system minus K r minus r0. Okay. And corresponding potential energy is half K r minus r0. Okay. So, that will be the energy change, potential energy change due to the vibration. So, we have a system when it will vibrate, its energy will change, mainly potential energy will change, and that is this. Okay. So, now we are interested to find out the states of the molecule which is vibrating. That means the energy levels with which energy this molecule can vibrate, whether it can vibrate with any energy or the energy is discrete, okay, is quantized. So, that's what we would like to find out, and that is similar to the rotation case. We have to use the Schrodinger equation and solve the problem and find out the solution. So, now this vibration of this diatomic molecule, okay, say it's a mass m1 and mass m2. Okay. So, one can reduce to a two body problem, reduce to one body problem, right. So, that already you know. So, this will be the reduced mass of the system, and it will oscillate, it will vibrate like spring mass system. Okay. So, its equilibrium distance is r0, its reduced mass will be m1 m2 m1 plus m2. Okay. So, now it is just simple harmonic motion. Okay. It is the case of simple harmonic motion, this spring mass system, okay, one body problem. Okay. So, spring, there is a spring constant K. Okay. So, it is oscillating. So, this will be the potential energy, and this potential energy, if you plot this potential energy, if you plot, it will be like this if you plot. So, this is the energy, and this is the distance r. Okay. So, this is the energy. So, this position is r0. Okay. So, when the at the r equal to r0, this energy is minimum. When r is changing, its energy is higher, but these are symmetric. Okay. So, this is the harmonic oscillator potential, or if the potential energy changes like this. Okay. So, this then we tell that is the simple harmonic motion, simple harmonic motion or simple harmonic oscillator. It is a simple harmonic oscillator. So, vibration of a molecule. So, one can convert this problem to a simple harmonic oscillator. Its behavior is just like a simple harmonic oscillator, and to solve simple harmonic oscillator, the standard problem in quantum mechanics, and solution is known to you hopefully. So, this energy expression, if you solve using this potential energy, if you solve the Schrodinger equation for simple harmonic oscillation. So, this you will get energy E v equal to v plus half h cross omega. Okay. So, this the v is called vibrational quantum number, like in case of rotational quantum number j we have used here. Similarly, v is vibrational quantum number. Okay, vibrational quantum number, and the energy of this oscillator or this molecule which is vibrating, its states or its energy level is quantized, and this energy levels will follow this relation. Okay. So, I will continue the discussion. Let me stop here. Thank you.